Hi, my name is Kevin Starr, and we're now on to Chapter 3 of the Single Loop Control Methods book. This is the chapter on process identification. This is where things start to happen. So I've got my sleeves rolled up and we're ready to go because this is where tuning starts. There are several links in the chain that relate a process to optimization. They go through several phases, from modeling to PID models, or modes, There's standard, parallel, and classical are the three very general classifications. We're going to talk about that in a later chapter. And then we get into tuning. That's where everybody wants to get to. So tell me the magic rules, and we can get into whether it's Ziegler-Nichols or Pod A or Lambda or direct synthesis or overshoot or whatever you want. We can determine that in the tuning area. But you can't get to any of these steps if you skip process modeling, and that's what we're going to cover. In fact, this one is so in-depth, we're going to break this chapter into 3 video sessions. There's going to be a session that deals with process transformations. How do we relate an input and an output? In other words, if you turn the steering wheel on your car, what happens? Is it fast? Is it short? You have to know that. Same thing with your process. But then what is the way that you identify it? How do you figure out what the dynamics of your process is? There's not a, you can't go to the pipe and look for what are your dynamics. It depends on so many different variables. There's Newton's laws of physics. There's all these different things that you can use. We're going to show you some very practical methods to be able to identify the process. Let it tell you what it is, and that's what we're going to talk about in this session. Then we will go into self-regulating models. First order plus dead time. We'll talk about that. Then we'll get into non-self-regulating models. Those are tanks. Tanks are a lot different in terms of the type of model that we're dealing with. And we have to understand that they are 2 different types. If we represent our process in the industrial world, 100% of the processes that you'll have to deal with, over 90% of those fall into self-regulating. Non-self-regulating is a much smaller class. So we're going to spend a lot more time focusing on process transformations in this session. The next session we will talk about self-regulating modes, and then we will combine the non-self-regulating with the actual tuning methodology. So here we go. As we get into this, we need to at least hit up on the terminology. At the back of this chapter it has all these terms, but just so we're going to be using these, but you'll see when I mention SP, I'm talking about the controller set point. If you see PV or MV, we're talking about the process variable or the measured variable. You'll hear me talk about a time constant. That's the Greek symbol tau. It's not a small t. Tau is a kind of a universally accepted term when we're talking about process dynamics. K and T are typically associated with a gain and a time. And then we'll get into, sometimes you'll see U as the term used to represent a controller output. Output of the controller, it happens to be the input to the process. And Y is a measured value. It's what's the input to the controller, but it's the output of the process. That's always confusing. Notice here that your ins and your outs and your outs and your ins can be, depending if you're looking at it from the perspective of the process or the perspective of the controller. So I'll try to keep that all straight as we move forward. You may see this little triangle looking thing. This usually represents a change in or a delta. It's a change, and we're going to talk about that. And then slope is M. So these are just some terms. They're in the back of this book just so you can go back. If you see me going through these terms and you get stuck, just flip to the back and you'll get caught back up. Process identification. If that's such an important thing, what is it? Where do we start? What do we do? Well, when we look at this, we have a process. Think of it as a box. This process, it's a box full of unknowns. We call those unknowns dynamics. Our trick in process identification is to unravel the mystery of what's in that box. What is it? How's it going to respond if I increase the valve? What will happen to the process? Will it go up? Will it go down? If I push my foot on the accelerator, will I speed up fast or speed up slow? All of those things you have to understand before you can start throwing tuning numbers at your solution. Process identification is a way of predicting how the process will respond under certain conditions. That's the trick. That's what we're going to try to identify. Is we're going to talk about the terms like a bump test or step test or energy injected into the process, and letting the process tell you. Yeah, you could use Newton's laws of physics, you could use first principles, you could use a conservation of energy, you could use differential equations, and that's hard. Or you can do a bump test and let it tell you, and we're going to talk about all of those different methods. A bump test is what we're doing here is this is your process. And I'm just, again, this heat exchanger is one that shows up a lot because it's an easy one to visualize. But this could be your foot on an accelerator. This could be your steering wheel on your car. This could be a valve and a flow or a level. There's a lot of input and output relationships. Process identification is a method to determine the probability that if I make an input of certain percentage that the output will respond in a certain way. It has to be repeatable and predictable, and we'll get into that. But here we're talking about an input where we're making a manual change. It would be like if you could go to the actuator and change it, what would happen? Now we're going to talk about there's safety concerns, and in some industries this just isn't allowed. But we'll talk about how you could go about it. But I like to present the most fundamental method that you can get to for identifying the dynamics. These question marks, you just don't know what they are. They depend upon so many different things. You have to inject energy into that process and let it tell you. That's process identification. Whether you do your bump test through a front plate of a controller or you go in and enter it directly, you are injecting energy into this system. And you're trying to identify what's it going to do. If I make a 5% change in the output, what's the process going to do? If I make a 10% change, what's going to do? If I go to a different process, every process, now there are classes. If it's a flow, it'll typically act a certain way. If it's a temperature or a consistency or a speed or a tank or a, you name it. If the flow is oil, it'll be different than if you're pushing gravel through a pipe. The dynamics are related to the process, the type of process, the actuation, the pump, the delta P, all kinds of things that you have to consider, but you can do a bump test and let it tell you. That's what we're after. Here's an example of basically what I would call an ideal transformation, where you can see this is called a step change, this controller output, where we took the output from one position to another position. That's called a step change. And you have a converter that takes that step change, typically in milliamps, and converts it to a PSI. It was an ideal transformation. There was no loss. So they look the same. This then goes to a valve. The valve moves into a position. Let's assume we have an ideal valve so that there is no inertia loss. So you can see that the shapes are relatively the same. The only difference is the scaling. Input, output, input, output. Now we get into the process. So my question to you is, why would the process not be instantaneous, just like these pure valves or pure instruments? Why is the process have this nice curve to it, which is an often very common process response? So what in the process makes it respond slow? The answer is inertia. If you thought about it, it's mass, it's heavy. Even if I flip this light switch on, it's so fast, but there was a little bit of time, and if these fluorescent lights were old, it would take a little longer. But those are called self-regulating processes, and the time it takes for it to settle is very closely related to the inertia or the mass that's built up in that process. We're going to talk about that. And now let's assume we have a perfect transducer to take the actual measurement into a sensed. We're approximating it through a transducer. So you can see here that if I inject a step change, it goes through all these different changes and I get a process response. Is it fast? Is it slow? Is it got dead time? All those types of things we're going to be talking about. Those are critical. Those are the dynamics. Those are the calibration setup. Imagine if you have a transducer. This guy right here is a measurement, has a 0 and a span and a high and a low value. And your operator calls, hey, that measurement's not reading correctly. You're like, that's okay, and you pull out a screwdriver and you start adjusting the 0 and the span until the measurement matched what the operator was asking. You say, okay, does it read what you want now? And the operator says, well, yeah. And you say, okay, it's done. Now those of you that do sensor calibration and correlation, how much validity do you have in that calibration method? 0. You basically are saying, what do you want it to read? Go. The right way would be to either take that out, take it back to a bench test, set the 0, set the span, and get the slope right and get the calibration correct before you try again. That's typically what happens when a calibration goes out. You have to do some work. But in the control tuning world, it's the same thing. If your operator says your tuning doesn't work, what do? We'll throw these numbers in, and if he leaves you alone, it's okay. What we're talking about is the same technique that you would use on a transducer to calibrate it we have to do for our tuning. That involves a bump test or identifying the dynamics of the process. Here is what we're looking at with a bump test. You have several different inputs. This is the most simple, like I was talking about earlier, where you just change, it's like a gain. You input a step and the step comes out. That's the process response. But that's not always what comes out. You could get this one I showed you, which was a nice smooth transition from one state to another state. But that's not always what comes out. You could get this condition where I make a step input and it just keeps going. Well, those are actually a little bit scary to work on, where you inject an imbalance and it just keeps going. The thing is you don't really know. You don't really know what's going to happen when you change that actuator until you change the actuator. You could get any one of these responses. And if you don't know the response that you're going to get, the tuning that you're trying to do will never hit the mark. You'll never get to optimization because you ignored this step. You have to know the process, you have to know the response, you have to know, I recommend doing physical inspections, going and taking a look at the actuation device to see what's going on. That's what we're talking about. And that's what we're going to talk about, is how do I do this bump test and then what type of process comes out. Each of these processes have different dynamics. A dynamic is just a number that represents, it's a number in an equation that shows me what would happen in this output in a mathematical sense. There's only 3 numbers that you have to know, and we're going to talk about those in just a minute. Those shapes are so common. There's actually 6 here. 1, 2, 3, 4, 5, 6 shapes are so common in the industrial world, they've been given names. So you can kind of name them, and then once you know the name or the classification of the process, you can understand the modeling type. Once you know the modeling type, then you can come up with tuning. That's the whole technique. The first one here is called pure gain. This one actually doesn't happen. You can get a pure gain process, and it's like a math block. You know, you're just multiplying. That's like a slope change. It's a pure gain process. It's very rare in the real world to have a no dynamic process. Unless your sample time is slower than the dynamics, it can look like it just changed instantaneously. There's a certain tuning technique for those processes. The next one here is very common. It's called a first order lag. Notice that the measurement stopped after the input stopped, so it lagged behind. It's called a first order lag. Sometimes you'll call that a single pole system, or a pole in a 1 over tau s plus 1 if you're interested. So we'll get into the time constant of the process. We have to understand, this is very common. These next 2 are actually related. They fall into the category of second order. All that means is it's got 2 humps in it. So you can see here the 2 humps. You know, it started off slow. Sometimes I'll call that an S curve. So it's 2 humps, 2 dynamics. Or this one is called underdamped. I can remember on a rainy day back when the cars had antennas on the, maybe people don't understand that analogy anymore, but my car had an antenna. Was driving down, a leaf hit the thing, and it just started oscillating. And as the leaf went down, boom, it went back into its normal mode. And I was like, hey, that's a second order underdamped system. That's what we're having here. Underdamped systems like to oscillate. And given the right conditions, they will. Those are you need to look at. Usually in the real world, when you have an actuator that results in an underdamped response like this, you probably have a valve positioner that's failing. And I would recommend fixing it before you move on. This one's actually pretty common, a second order overdamped. Damped is a tendency, a second order system wants to oscillate. Dampening has to do with your attenuation of the oscillation. So if it's overdamped or over-filtered or over-suppressed, you get this response. If you are underdamped, you're taking the filtering away and it tends to want to oscillate. They call that a zeta factor, but if it's 0, it'll oscillate forever. Anyways, that's second order, and we're not going to cover those in this session. Integrating is the process that when you have an inbound, like a tank. A lot of tanks fall into an integrating process where I make a change and it just takes off. Those are a lot different, and we want to I wouldn't recommend starting on tuning tanks. There are some tricks that we learned since the first edition of this that can make tanks much easier, and we're going to couple identification of tanks and tuning in a separate segment. This guy is very common. It's called first order plus delay. In other words, I made a change and I had to wait for the change to hit to get there. It's a dead time. It's a delay. That's what we're talking about, is the models. So understanding the different classification. There's pure gain, there's first order, there's second order overdamped and underdamped, integrating, and first order, plus dead time. What we're going to cover in the next session is how to identify first order plus dead time, these three models. And then we'll couple integrating, and then we'll get into tuning. Now, this picture, I already showed you the transformation from the process where we went from an ideal transformation, where you can see I had an I to P converter, a valve, an ideal valve. We have some sort of a process. This would typically represent a flow or a pressure or a consistency or something like that. Even a drive sort of has this sort of dynamic. And then you're measuring it. It could be any measurement. But you can see there was the input was a step change from 4 to 20, which I don't recommend. That would be 0 to 100%. I'm just showing you an example. And you can see the output went from 3 to 15. The valve opened all the way. The process changed. So here you have how many lags do you have in that first how many lag is when the measurement stops after the input. So, okay, if you could imagine a dotted line, the input went right here. So the input was done here, but the measurement, so that's a lag. It lagged behind. So how many of those lags do I have in this process? Just one. So that's why we call it a first order lag. Just one, and that's a fairly simple process to identify, and I'll show you that in a minute. This one's more realistic though. You never have ideal valves, you never have ideal transducers, and you don't have an ideal sensor. So here you can see, you know, this one in today's stuff, this is pretty good. I've been to places where the I to P was bad, and this was the biggest lag of the entire thing, which it dominated the whole process. And when we get into nonlinearities, I believe it's chapter 9, we'll talk about that. Valves, they're wonderful and nasty all at the same time. You can have single-seated globe, double-seated globe. You can have rotation, pinch valves, rotating valves. You know, there's so many different types of actuation devices, and you know, there's maintenance required. There's actuator positioners. This is not uncommon that there's a delay. Now, with the advances in actuators, they're a lot faster. They're a lot more precise. You have to deal with that. That's another dynamic. And then your process, let's say it's exactly the same. Well, now notice how many lags do I have? Well, I have the lag now from the valve, and I have a lag from the process. So now no longer is the process seeing a step input. Notice the process is seeing a first order input. So we had a step change. We had another step change, but because the valve's not ideal, it lagged behind. Now that it's lagging behind, the process lags behind. And then even if we had an ideal valve, we get, how many humps do I have? 2. This is called a second order response. You'll see here in a minute why that's important. Once we identify the order of the process, that tells us the dynamics that we need to solve for. In the world of control and process, there are 2 dominant classifications. I showed you 6. Those 6 can be mapped into 2. The first one is self-regulating. The second one is non-self-regulating. Just want to spend a minute or 2 talking about that. This one shows, if you can look at this, the Newton's laws of physics, and that's what I recommend, that you kind of take a picture of the control loop that you're going to tune and visualize it, draw it out. What governs the level here? So let me ask you another question. What determines the outlet flow? What are the things that determine the flow of liquid coming out of this tank? Just, what do you think? Just, you can write them down right now. There's like 2 or 3 things. Well, this one, there's a restriction. So if this thing imagine if it shut off, there would be no flow, okay? That's one thing. What's another thing? One of them is called the tank level, or the head, the pressure head. The higher the level, the more pressure, the more flow, okay? Well, what governs the level? Well, this inlet flow, all right? So if I do a change where I increase the inlet flow, what's going to happen to this flow? Well, it's going to go up. Once it goes up, what happens to this tank level? It goes up. Now that I have more pressure, what's going to happen to this flow? It's going to go up. But what will eventually happen is it'll hit a state of equilibrium. And that's what's called it will stop itself. That's called self-regulating. Now, for this example, if I put a controller on here, I break the self-regulating nature, and I decouple the inlet and the outlet. So if I increase more fluid, this tank will just overflow until it empties. That's the difference between a self-regulating and a non-self-regulating. And this one, remember, self-regulating, Non-self-regulating, now what happens is as the tank level changes, the pressure is changing, and this controller is seeing that, and it's closing this valve as a proportion to this level. This is called non-self-regulating. It is important to know the difference, and you'll find out very quick. If you don't know to do a bump test, you'll find out pretty fast. If you had two tanks feeding each other, you can see this is a self-regulating, this is a second order. So you can see how it would have looked like if there was no lag. And there's a lot of physics here that we can look at. If we knew the size of the tank, we knew the volume, we knew the restriction, we could calculate all this. We would never have to do a bump test. That's called first principles. First principles, or Newton's laws of physics, says you could write the differential equations, all this stuff down, and you could calculate the process model. That's just really hard to do. It's much easier to do a bump test when possible. One thing to keep in mind when doing a bump test is perfection is not required. You can map everything down to what's called a simple process model. The simpler the process model, the better. Now, as you get more elaborate and get more requirements and more tight tolerances on the control strategy or the control performance, you need to move your modeling methods to more complex models. But I want to introduce the concept of model mismatch. Model mismatch is when the simple model and the actual model don't match. A simple model being a first order, which is that one that has the curve in it, the first order. Notice that's this dotted line in each one of these. That's the first order curve. Assume everything's first order. And then what you have is you look at what actually happened. And then you fill in the difference. And that's called model mismatch. We're going to use model mismatch as a calibration to our tuning when we get there. So don't freak out about having to know every single thing. Those are for later courses, and there are methods that can show you exactly how to come up with models for all this. But for this class, there's two things you have to keep in mind is how far did it go and how long did it take? Those are the two things. Notice in every one of them, how far did it go and how long did it take? How it got there can be different, but those two dynamics are what you need to know. And then you couple that with model mismatch, and that's what we're going to get into. Now, how do we do a bump test? Remember this poor guy, he's looking into this process trying to figure out what's going on. A bump test is a way of injecting energy into this process so you can kind of see we're in it and we're watching it. Now, I've done bump tests where I've done a stopwatch and I've watched it. I've always found that interesting. This guy has $1 million system and he's using a $5 watch to tune it. There are methods that we have, there's tools that we have as part of ABB that allow you to calculate this easily. I love those tools, we wrote most of them, but if you don't know the fundamentals, how do you know if the automated system's even giving you the right number? I recommend that after this session that you go and do a few bump tests on some non-critical control loops. Back in the back end, or set up a simulator, or set up a lab system, or something in your control, in your instrument shop, where you can play a little bit to do a bump test and watch the process and calculate the process response. How far did it go and how long did it take? That's what we're going to get into. But you saw this one. This is just an example. We walked up, we did a manual step change, change the valve, and then we watched the process. If you can get a trend, I see trends better than numbers, but that's just me. I also recommend this bump test methodology. This is where when I first started doing these, you kind of forget that you're making a product on the other side. So if you always bump in the same direction, you can get yourself in trouble. So what I've done is I like to implement this bump test strategy where if the first bump, whatever you pick, 5%, do it. Then when you go back the other direction, go 10%. Then go back to 5%. That way you're always bumping right around the steady state dynamics of that process. This is where there's a lot of work and trust that you need to build up with your operators. A lot of times the term bump test is a little scary. I mean, you've got a critical process and they envision you with a sledgehammer just banging that thing. That's not what we're talking about. We're talking about take a look at historical trends. Take a look at how much that output has been moving over time. Don't go in and make a change bigger than that. The trick is that you have to make an injection of energy into the output that makes the process move just beyond the noise or the normal ebb and flow of your process. That takes a little bit of effort. And I recommend that you talk with your operators and you ask them, where's our defect limits? Let's bump in the direction away from the defect limit. Let's try to figure out how to not cause off-spec production just because we're doing a bump test. Once you start a rapport with your operators, this isn't a big deal. Usually that's one of my kind of litmus tests when I go into a plant, is if I talk to the operators about doing a bump test and they get very apprehensive, then I know that those loops have probably never been tuned. If they say, sure, let's pick this one, I'm having trouble, then I know they understand, and we make sure we don't do bump tests that would cause them to make an off-spec product, make them break down, or make them have an explosion. Now for those cases where it's just not possible, there are other techniques that are a lot more difficult that require a lot more trial and error. And we'll talk about that in a later session. Right now I want to focus on you understanding that there's a bump test. That's a way of injecting energy in a manual mode. Whether you do it through the operator station or go to the valve itself or the final control element, I recommend that you do this bump test cycle. And there's always caveats. If you've got a valve that's geared, you kind of want to make sure that the hysteresis and stiction are worked out. So you may want to do a couple of steps in the same direction, almost make like a triangle, so that you can make sure that the play's out of the valve, and then when it turns back the other way, you can start telling if the gears are working. But the idea is don't leave the normal steady state mode that you're starting with. So some of the hints is work with your operators, figure out where the off-spec limit is and go the opposite direction. Look at a trend of control performance and see how much has the actuator been moving, and move just a little more than that so that you can, and I would always start small. And if the operator says, hey, I can only let you do a 1% change, if you do this, you can actually do a 2% change, but you never left 1% from where you started. Typically what we find is this one is usually not quite enough to identify the dynamics. This one is usually a good one. Don't just change the actuator by 50% and see what happens. You really want to make an output that is representative of normal control actions. That's the bump test. That's process technology. And what we're going to do in the next session is we're going to loop these first three. Pure gain process, what are the math? What is the gain? What is a number that represents this process? A first order model, what are the numbers that define how much and how long? And then first order plus delay is I made a change, nothing happened, then it goes up. Well, how do I identify all that stuff? That's in the next session. And then we will talk about integrating tanks. How do I come up there? You have to calculate slopes. So those are what we're going to cover. So this has been the session on process identification. Why is it important to come up with a dynamic? That's the cornerstone. That's like the calibration step. If you skip that, you're kind of guessing. Recording that, making sure you have a report, that you document it, so that you go a week from now or a month from now and an operator says, hey, this loop is broken. Do a bump test and compare the dynamics. Typically, the dynamics change. The controller is zeroed in, and when the dynamics move outside of what the controller is looking at, that's when instability happens. So get in the habit of recording your tuning parameters, the time, the date, the inputs, so that you have a track record. So when you come back, you can say, oh, if the dynamics change, then you can do adaptive control, predictive control. There's a whole bunch of stuff. But if you don't keep track of the process dynamics on a regular basis, you're flying blind. That's where the first step. That's why I said we're rolling up our sleeves and we're digging in. So let's get through the process section. Let's start thinking about a loop that you would like to tackle. And now let's move on into identification. So now that you have your bump test, you did your step test, you have your response, whether you have a trend, I would recommend that you come to the next session with a printout or an example, and then we'll tell you how to put numbers on those to come up with, well, what is it? That's this session. Thanks.